to be a continued trend. So that's why I specifically want to check 45, because it's like it's a pretty big one. And then that's the one I want to check, but I'm going to check them all. Did I just start this video? Okay. So, did you guys get my alpaca picture? It was awesome. You guys missed out on the alpaca show. We were there for way too long, but yeah, it was cool for like the first hour. Okay, so in light calculations from wavelength to frequency, you're just going to be taking the C is equal to HB. C is equal to lambda times frequency. So I just showed the rearrange equation, but in the end, make sure you put your units so you can stack them correctly. Nanometers cannot get plugged directly into the speed of light equation, so you have to convert to nanometers first, and then you end up with 3.8 times 10 to the 14th hertz or per second. Thumbs up? Okay, so that's a simple one. That's an honors chem question, as is 40. The only weird thing about 40 was that you had megahertz. Mega is a prefix from like the metric system, which is how many away from base? 6 zeros, which means 10 to the 6, right? So what number of times bigger than base? Say again? 1,000,000 times bigger than base. So 10 to the 6 is equal to 1 mega. So that's going to get you to hertz, which is like the very basic form of frequency, named after Mr. Hertz. That's the same as per second or 1 per second. So when you plug that frequency into the speed of light equation, you get approximately 3 meters. Does that make sense for a radio wave? They're very long, right? So they're longer than we are in some cases, or longer than we are tall. So that should make sense, especially since we're dealing with radio. The other one was like a laser, so it's gonna be short. This is the big one, okay? So first you were like, what the heck is a work function? Solid elemental lithium, blah, 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 blah. If you look for the key points, you can dumb this down to a doable question, which would be 279.7 kilojoules per mole. That's the energy requirement to remove 1 mole of electrons. So that much energy is required to remove 1 full mole of electrons. So if you scale that down to a single atom, you're basically looking at Avogadro's number and how that relates. So this is kind of what that first question, or for the givens were, and it was talking about lithium, releasing 1 mole of electrons can make lithium ion. So we'll start talking about that as called ionization energy this week. And so it wants you to know the wavelength that would deliver that amount of energy to bounce those electrons off the lithium atoms. So I set up a proportion first, kilojoules to mole, which we don't work in kilojoules a lot in the energy form. We work in joules because that's just the relationships that we have with these equations. So if you just immediately convert kilojoules to joules per mole, you can then break that further down to joules per atom, which is the question. The question was talking about removing an electron from an atom, which is why you need to bring it down to just the atomic level. So joules to joules per mole to moles per atom is going to cancel out moles to give you 4.6 times 10 to the negative 19th joules per atom. And that is literally energy. That is E. Hang with me for a second, ladies. You good? Well, hold on one second, okay? So, because you can't hear if you're talking over me, okay? So E is energy, and since E is energy, you can plug it into either the energy equation and then the light equation, or you can rearrange like we did on Friday to relate wavelength to energy, which is what this big mess here is. C times H over the energy of this wavelength. And so when you convert that to wave, 4.3 times 10 to the negative 7 meters, which some of us are more familiar with the nanometer wave range. Do you guys know what color light that is? Violet. That's on the 400 side. 400 is violet, 700 nanometers is red. So that's really high energy light, which is why it's able to deliver the energy to lithium atoms and then bounce their electrons out. Questions right here.
I just didn't realize.
Oh, and number in 30 whatever. Gotcha. Okay. All right. So when they give you kilojoules per mole, and it's questioning about atoms, just remember the relationship between moles and atoms is Avogadro's number, and break it down to the atomic level. Did that part make sense now that I've shown that to you? Who got this without me? Okay, just like not very many of us, but I feel like this was a good challenging question with some review. Give me a thumbs up when I can move past this. All right, so are you guys a fan of this equation? Pulling everything together versus doing it twice? I am too. I don't tell honors came that. I'll let them figure it out if they want to. Okay. 52, you just had to just basically figure out how much energy was released from the transition from energy level 5 to 4 as an electron dropped, or 4 to 3 or 5 to 3. So these are 3 of the same exact questions, but I'm just going to show you the answers so you can check yourself. But as you look at the energy release, what equation will give us that information? Say again? Rydberg's equation. So once we get that energy, we can convert that to wavelength very easily. So, energy of photon, Rydberg's constant, n final squared over, or 1 over n final squared minus 1 over initial squared. So plugging in that information, you get all these joules of energy released. What does the negative really just mean to us? It's released. That energy is not truly negative. E is never negative. It's just a quantity that says how much energy is released or gained. And so those energy values, you can plug directly into the wavelength modification of energy and wavelength. Again, C times H over E gives us wavelength. So making sure you plug in the calculator right, all your units cancel. You should get wavelength for the first one, 1.88 times 10 to the negative 6. The second one, 4.06 times 10 to the negative 6 meters. And then the last one, 1.33 times 10 to the negative 6 meters. Those were all, most of those dropped to 3, right? So the first and the last one dropped to 3, which whose series is that when you drop from a high energy level to level 3? Megan? Say Paschen series, right? Which is the IR wavelength. The only one that you could not predict from that little mnemonic device I gave you was the 5 and 2, or 5 and 4. But what you can imagine is 5 and 4, is that a big drop in energy? No, so it's still going to be on the low energy side of the EMS, which is, in this case, it does correlate with IR, because those are all really close. So what's the one called when you drop to 2? Balmer series, which releases what type of light? Say again? Visible. And then what's the one that drops all the way down to 1? Say again? Lyman, right? Okay, sorry, I hear you guys, but I can't hear you guys. Again, what kind of energy is that? UV, which is of those 3 types, is it the most or the least energy? Most, right. Okay, can I go past this? Okay, so that was 52. So 55, I didn't copy this question here. It asked about, does this drop have enough energy to be, what was, tell me the question.
Do these drops have enough energy to be visibly seen?
To be visibly seen, okay. So when you're dropping from, actually no, this is not dropping. This was jumping. Read the question, like full out read the question to me.
Does a photon of visible light, 400 to 700 nanometers, have sufficient energy to excite an electron and hydrogen from
Blank to blank. Okay. So basically, does the light have enough energy to cause this excitation to occur? So you basically were, given the fact that you only knew this information about N and N, you had to plug it into the Rydberg equation, figure how much energy was required for that jump, and correlate that back to, does this energy correlate to the visible light spectrum? And this particular one required 2.09 times 10 to the negative 18th joules. Since you can convert that to wavelength quite easily, you find 9.5 times 10 to the negative 8th meters, and the visible light spectrum is in the meters to the negative 7 to the negative 7, so it's like 4 times 10 to the negative 7 to 7 times 10 to the negative 7, because that's 400 nanometers to 700 nanometers. So this is outside. Is this a higher or lower form of, is this a more energetic or less energetic form of light, invisible light? Okay, so it's a more energetic form of light. Hold on, I just, so it is a smaller wavelength, so it should be able to actually excite that. Just look back at my old stuff. This was me like 4 days ago. Question is 55. And why are we not enough it is outside of the visible light realm, but it's more energy. So truly, it should be in the UV side. So it should be enough energy. That's lower. That's a little.
Isn't that higher what it needs? So that's, it needs more energy. Since visible light only 400, so it has less energy than is needed.
But no, visible light's 400 nanometers, which is wavelength. So this is because visible light is 4 times 4 to the negative 7 meters to 7 times 10 to the negative 7 meters. I like to question myself writing for ideas. So if that is a lower, that is a shorter wavelength. That should be of higher energy. But did it specifically say visible? Yes. Okay. Well, it's out of the visible, so but it should be of higher energy. Yeah.
I just flipped the equation and I solved for E and I plugged in one of the values, I did 5.5 times 10 to the negative 7 for your wavelength, and then that's the energy you have, and you'll see that it's less than what's required. So
Okay, I'm gonna say with my initial answer, I'm questioning myself out loud, so we'll come back to the why. But on the other one, you're dropping. You're jumping, and it requires 4.84 times 10 to the negative 19th joules, which is in the visible spectrum, which follows the qualifications of why something is delivering enough energy for that jump to occur. Okay, but out of everything, this one I think is the one that you should look into, studying for a test or for situation the most. Because one, looking at your reference table, do you guys have a reference table nearby or have somebody? What is provided to you on there regarding light? Those two equations, right? So C is equal to lambda times frequency, and E is equal to HV. Do you see Rydberg's equation? No. So on an AP exam, they would not have. They wouldn't require you to memorize Rydberg's equation for you to use. But if they're giving you those equations, they'll ask questions like this, which is what I will try to mimic on your test. Okay? All right. So, flame test lab for 15 minutes because I have had way too many requests for this. And then we will do quantum. Okay, quantum mechanical model. So, read instructions on board. Follow into the back. Get some goggles on. You just need like one piece of paper. I don't think you're in half with somebody. That's what that is exactly reading this lab. Googles.
I don't know how to do it.
Alright, you have about 3 seconds to get your body settled in a location with goggles on, ladies. Goggles on. Alright, so I'm orally telling you how to set the Bunsen burner. Look at the butt. The butt is the little gas intake valve on the bottom. Look at the butt. So turn that thing up and look at it. Turn it up. Face the butt. The butt should, thank you. Okay, so looking at the butt, righty-tighty all the way. That means the valve is closed all the way. Lefty-loosey, a half turn, which is 180 degrees. But you might need to go a little bit more, so maybe like 270 degrees. Only because sometimes they get a little gunky and they don't actually let enough gas come through. Please be quiet so we hear these instructions. Now, looking not at the butt, looking down the barrel. So you're looking down the barrel, righty-tighty, all the way. That means you're cutting off all sorts of oxygen for this fuel, meaning it will not combust with a strike. So you need to open up 4 full turns to the left. Lefty-loosey, 4 full turns, also 8 half turns. And that should be an adequate amount of oxygen to allow for combustion to occur upon the spark. send somebody to me to come get a striker. Remember, 3 strikes, you're out. If you're out, you cut the gas off. How do you cut the gas off? You turn the gas jet off. You don't turn the Bunsen burner off. The Bunsen burner is not your. You don't enable it from the striker. Alright, and hold on, do not strike yet. Okay, so one, ladies and gentlemen, pull your hair back, tuck at the back of your shirt. I don't want to have any burnt hair smell in the room today. And then if you cannot strike very well, get a good like practice running for striking. Because if you stand over it, you and you don't make any strikes. You're not making any fire. Okay? So you also have to get that face lift. Get a lift. You want to get your loose home. Wait, hold on.
That's loose, so that's loose.
Wrong way. You got too much gas in there. Too much gas.
No, wrong way.
You guys need oxygen.
That happened.
You guys need
Take that finger fire, that's when the mate's talking.
Alright, I'm cutting the lights down so you guys can begin. You're reading down, I'm sorry. You're gonna shut that door, then you grab.
Yeah.
Alright, you should have an inner loop home, and if you do not remember how to do this, all you're doing is dipping your loop into the solution. The loop is what's going to be inserted into the inner loop home. The loop can only stay in the inner loop home for about 3 seconds before the solution just burns off because, you know, it's hot, it's evaporating. So if you didn't catch the color, you gotta dip it again. If you didn't catch the color, you gotta dip it again, okay?
The solution part is very much right.
There are more solutions at other stations, so feel free to walk and ask for other solutions.
Everyone watching?
It's actually really good.
Why are you slow? Wait. Last whole thing?
I didn't catch it. So what color is it?
I'm
Flash the video.
combination of me and CJ.
It's like a magenta. It's not magenta. Another one has a
CJ can't see me.
No, we're looking at the outside of the river. It's just a matter of what you see. It's kind of like at the top, so you can see the whole thing. You see the, like, you see the color very, very. Well, no.
you wouldn't have, if you see yourself identified with green color, you wouldn't have a solution for identity.
Alright, you should have like 3 identified so far, identity and color. You can get 3 more, you have a total of 6, and then what do you want?
That's white, purple.
There's plenty across the room.
Black, white, purple. What? Boy, some of them Chase,
Like sulfur. I want that like
Does anybody have lithium chloride?
There it is.
Alright, and there's one strontium chloride is a bunch, so if you didn't get strontium, there's only one, so you just have to hunt.
This one's in the fun. I can feel why. It's that wasn't water. If you go pink, red, arrow, Real yellow. Yeah, a whole bunch of Crayolas out here.
Alright, you got 3 more minutes and then you're gonna this lab in the box.
3 more minutes left. I'm going to survive. You gotta drop pictures. You gotta drop pictures.
3 more minutes and stop in the box.
No, it was red. That was good. All right. Gatorade. This is called this time, right?
Everybody, strontium. Strontium. Raise your hand,
We
you have
have
a strong hand.
strong,
JT's your.
Arms, right? Watch this, watch this. Oh. No, come on, man.
Yeah, that is.
What did you say? We're gonna do a bubble too.
Alright, I'm gonna turn the gas off in like 30 seconds.
Wow.
William, are you done? Okay. I'm turning the gas off in 30 seconds. Keep the gas flame.
We have to.
Good conversation. Alright, count your flame solutions back in the buckets and bring me the buckets here, please, along with your strikers. That's what you do this collaborative. So, don't hurt there. Put your strikers back here too.
Hey, there's something basket, please.
That was like, so that comes from that. But also, yeah, it's like, I'm mad at you. Wow. I need a little bit light. It'd be a nice little censure Picture what you see describing around the
Alright, you have 1 minute left in the box, and then come on back up here. Come on. This should be a quick and easy exercise. Alright, back up here in 10, 9, come on. Grab your notes, we're gonna start quantum. Quantum. Chase, you can take your goggles off. You're safe now. Okay, so here we go. We've gone through like 100 years of history. We went from the blob of Dalton to who is next in terms of the atomic model and the history of the atomic model. Thomson helped with developing or helped the identification of the electron, which we thought was the atom, and he made the what model? Plum pudding model, and then who came after him? Millikan helped describe a little bit more about the electrons. He described the mass to charge ratio. Like, we know mass of the electrons pretty dang small, but he helped describe that. After Millikan was Rutherford, which did some alpha particle shooting at Goldfoil, and he discovered the nucleus. And then we discovered after that, Goldstein helped Rutherford, but Rutherford started it. They helped discover the proton existed inside the nucleus, and then not Bohr. The name starts with a C. They're what you call the ballots, little things you punch through the ballot. Chadwick, okay. Just trying to give you clues. Chadwick, which helped determine the presence of the neutron, the only other subatomic particle, right? Okay, so he had discovered the neutron, and then Bohr was like, oh, I have an idea. There are energy levels around the nucleus. And then we were like, psych, that's only true for hydrogen. And then Schrodinger et al. Came along and said, there's more to the story. Yeah.
Last year, I know you had that charged mass on Mars, and you like don't look at it. Everybody have to look at it.
Yeah. Okay, so Schrodinger and his friends helped develop the quantum mechanical model. I'm essentially going to describe to you the big ideas about the quantum mechanical model, and then what quantum numbers are. So we have a general idea of why we're describing things with S, P's, D's, and F's. And then what we consider Pauli exclusion principle to really mean, so that it helps us understand something a little bit later this week. Okay, so he basically said that electrons can act as a wave and a particle, which gives us the idea that there's something called particle-wave duality, which essentially says exactly what it sounds like, means what it says. Duality means two. If you have a particle and wave duality, that means that you are able to act as a particle and you're able to act as a wave. If you're able to act as a particle, that essentially means that you have mass and volume. Mass and volume is just, you know, the two properties of matter. Like electrons, they are matter, right? Electron lives matter, right? They have a little bit of mass, which means they have a little bit of volume, but they're not only acting particularly, they're also acting as a wave, or they potentially can act as a wave. Which is why we can describe electrons creating a certain wavelength of light, or having a certain frequency, or having a certain amount of energy. That's what the particle-wave duality means. It's just dual nature. So, since they have this property, we can really discern a lot about electrons and how they move and how they behave. But where are they? They're really around the nucleus in electron clouds, which the clouds get bigger and bigger and bigger and bigger as you form larger and larger and larger atoms. So far, this makes sense? Bigger atoms, bigger electron clouds. We call the electron clouds a probability distribution because we say, like, there's a 99.9% probability it's in this cloud. There's a 99.9% probability it's in this cloud. Because, did I tell you guys my joke, Heisenberg? No? Okay. So Heisenberg's principle is the more you know about the velocity of an electron, the less you know about its location, exact location in a cloud, and then vice versa. The more you know about where its location is, the less you know about how fast it's moving. So Heisenberg and Schrodinger are going down the road. Whoop, whoop. Police car pulls him over. Sir, do you know how fast you were going? No, sir. He's like, you're going 900 miles an hour. They're like, dang it, now we're lost. Yes? Do you get that now? You don't just have to laugh. You have to get it. You get it, okay. So you know how fast you're going, but you don't know where you are, or you know where you are, and you don't know how fast you're going. Okay. So the probability distribution is just like, we think the electron's in this cloud. Right. I told that to honors chem, and like half of them figured it out, and I was like, we're going to move on. Okay. So that's the probability distribution. You guys okay? Are we explaining the joke?
The more you know, the less.
The more you know about one, the less you know the other. The more you know about how fast you're going, the less you know about where you are. Woo, okay, we got past that one. Okay. So I'm going to draw a picture over here. This is the probability distribution. You can see like it's very much a scatter plot because they're saying we're pretty sure the electrons either here or here or here or here or here or here or here. There's a big blob, so that's we can't pinpoint it. But we say in this general cloud region, there's a 99% probability where the electron exists. So what we say is that the cloud, like this cloud, is supposed to be representing the 1s orbital. It's kind of spherical in shape, and it's the first energy level, meaning it's just a singular unit of distance away from the nucleus. So we're going to call this n equals 1, which is the first energy level. And then sequentially, you can draw the second energy level, and your cloud would be out here. So that goes on and on and on. But what this is supposed to be indicative of is just hydrogen, because hydrogen only has one electron. We're just putting in the first energy level. So the distance the electron is from the nucleus is going to be the cloud. Yeah.
Wait, so like, how would you be able to tell the difference between like hydrogen and helium?
You'd have to know how many electrons were there. You couldn't tell just from the cloud model. Yeah. So if you saw that word highlighted, it's my favorite awkward term, nuclear penetration, which is going to talk about how the nucleus, you got your calculator there? Okay. Talks about how the nucleus is in the middle. It's a positive charge, right? And then you have n equals 1, and then n equals 2, and then so forth, n equals 3 and on. Who's the closest to nucleus? N equals 1 or 2? 1. Okay, so electrons and n equals 1, because they're so close to the nucleus, they have a very, very strong attraction. We're going to relate that back to Coulombic attraction. What was Coulomb's law? I'll get you started. Force. Force doesn't equal mass times acceleration, but not in chemistry. Force equals K, which is a constant way. We don't really care about K. Keep going. Q. I'm going to say plus because that's our protons, or nucleus's charge. Times Q minus, which is the charge of the electron, over distance squared. Okay. So Coulomb's law of attraction means that the closer you are to the nucleus, or sorry, the closer your two oppositely charged particles are, the more force of attraction they have. So because of this like insignificant difference in their distances, we say that n equals 1. The electron there undergoes nuclear penetration because it's going to be actually further pulled into the nucleus's region because of that strong attraction. Where n equals 2 undergoes less nuclear penetration simply because of its distance being so much farther away. So you can see the evidence of that here. So this is supposed to represent the radial probability, which tell me what that means in real people terms. Radial, what do you think that sounds like though? Okay, the radius, so how far like what the radius is of that particular cloud versus, the distance of the cloud from the nucleus. So we're hoping that these correlate, which they do. The nucleus, or the 1s energy level is really close to the nucleus, so it's radial probability where the electrons are really close to the nucleus. And then the second energy level is much farther away from the nucleus. And they have more space to play in because simply your radius is bigger. So that's why it's got a larger hump. So we won't see these graphs too frequently, but that's what it's referring to. And then, since we're still talking about the quantum mechanical model, we're referencing Bohr because Deanna got this whole thing started. But essentially, Bohr's only work for hydrogen. The quantum mechanical model works for all elements plus hydrogen. And we don't call the energy levels orbits anymore. We call them orbitals. So that's where we are right now. We are now in quantum mechanical model. Yes? It just means charge. So like the charge of the nucleus is positive, the charge of an electron is negative, so I just put Q plus and Q negative. Or like if you had 3 protons, you put a 3 plus, versus looking at the attraction to 1 electron, you put 1 minus. So we will put numbers in there at the end of today if I get to it today. Okay. Okay, and I think I pick up, no, not quite. So I'm almost to the place where we are in your notes. So I wanted to show you these radial probability graphs, how they differ for each element, because this is really where the Coulombic attraction comes into play. So helium, neon, and argon all have their 1s, 1s, and 1s at a different distance from the nucleus. Turn and talk and think if you can tell why that's the case. Alright, I'm hearing good things. I'm just gonna align my board real fast. This thing is. Alright, everybody look at helium. Come back to me, come back to me. Helium has how many protons? Two protons. Neon has how many protons? 10 protons, and argon has 18 protons. Okay, so if the nucleus is highly charged, what is it doing to its first energy level? Like super duper attracting it, right? It's making the first energy level undergo a lot of nuclear penetration, which is what's that going to do to the energy level cloud? It's going to shrink, right? So it's going to get smaller, which means its distance from the nucleus is going to be smaller, right, or shrink. So helium's way over here. That's a pretty large distance. Neon's about half that, and then argon's is super, super, super close. So who's undergoing the most nuclear penetration? Argon's first energy level, right, 1s energy level. And it's simply because of something called ZEF. Do you guys remember what Z stands for? Proton number, right? You should know this now. ZEF, Z-E-F-F, means nuclear, effective charge. I'm teaching this in honors school today. I just had a brain fart. So the EFF refers to effectiveness, like how effective the nucleus is at attracting its first, second, third, and fourth, whatever, electron clouds. So nuclear effective charge is what ZEF stands for. And the higher charged your nucleus is, meaning the more protons, the better it is at effectively attracting its first energy level. Opposites attract, right? Yeah.
So even though argon is one of the bigger ones, it's not gonna, like, it's gonna have a smaller cloud.
Only its first energy level. Notice, yeah, so that's why I specifically wanted you guys to look at the 1s, because you're right, argon is relatively larger than neon and helium, but that's its overall huge, 3p6? Its third energy level is way larger than all the rest of these, but we're looking at the first energy level. Okay, can I move on from here? All right, just note what ZEF is. Let's talk about that more. Okay, so all that kind of builds up to the quantum mechanical model, and what we care about with the quantum mechanical model, they just care about where electrons are. So I can give you an address for here, okay, my room, but we're going to start out big. So I can go, okay, USA, then we narrow it down to what? North Carolina, then we narrow it down to? Okay, maybe like Cabarrus County, and then Concord, and then, okay, maybe like Cox Mill Road, and then Cox Mill High School, okay, Science Hall, and then, 1627. So we can look really broadly at where we think people are. Like I could say, yeah, Jillian's in the United States, but that doesn't really give me any indication of like exactly kind of getting close to where she is. So that we do the same thing for electrons. Sometimes we just care like, hey, what energy level are they in? So if I care about what energy level they're in, we call that the principal quantum number. So like if you're in the valence shell, you might be in n equals 4, n equals 5, or n equals 3. Doesn't really help us a whole lot. We just know generally your distance from the nucleus. We can get more specific though. So if we go to the orbital number, or the angular orbital quantum number, it gives us the shape that you're speaking of. Are you in the S, P, D, or F-shaped orbital? Do you guys remember the shapes of these? Yes? 3 people said yes. Okay, let's quickly review that. So S-shaped orbitals are what shape? Spherical. Think 3D, right? So S are spherical. P orbitals are dumbbell. So I'm going to draw that in all the orientations they can take on. So P orbitals come in a P. What axes am I on here? Y. Okay, I should have started X, but sorry. Hence says 2020. It can also be this way, which would be P X. And then if I come out of the board and into the board, that's PZ. Okay? So P orbitals, or the P, actually I'm going to write this as set level. The p sublevel has 3 p orbitals. Okay, the s sublevel has how many orbitals? 1. You can't take on any more than that because the sphere can't come in any other orientation. It's a sphere. All right, so that's 1 s orbital. All right, so the s sublevel has 1 s orbital. The p sublevel has 3 p orbitals. The d sublevel, I'm not drawing all of these just because, okay? But they come in a double dumbbell form, so it's like 2 dumbbells like that together. And just understand it does not, you can label them as x, y, and z, but it's like dxy, dyd, dxz, dx squared, y squared. They have really funky notations. But how many different orientations should there be in the d sublevel? 5. 1, 3, 5. Is this becoming, you see the pattern? Okay, we're adding 2 each time. And then there are 5 d orbitals. All right, so then in the f sublevel, which it looks like a flower, okay, so it's like dumbbell 1, dumbbell 2, dumbbell 3, dumbbell 4. But that can take on 7 different orientations. Okay, so this is 7f orbitals. All right, so where else in our chem life have we seen 1, 3, 5, 7? As of recent. 1, 3, 5, 7 orbitals at that. Not just electron configurations, but what do we draw regarding electron configurations? Orbital diagrams, right? So when you hit the 1s orbital, how many orbitals do you draw? 1. When you hit like a 2p orbital, how many orbitals do you draw? 3. When you hit the d block, how many orbitals do you draw? 5. When you hit f block, how many orbitals do you draw? 7. That's why. 2 seconds. 2. Okay. So the magnetic quantum number, which is what we've actually just been describing, just tells us which orbital of the 1, 3, 5, and 7 we're speaking of. And then the 4th quantum number tells us, are we talking about the electron that's spinning up or spinning down? Remember in our orbital diagrams we were drawing ups and downs? So I call them up and down. Truly you could label this clockwise or counterclockwise. All right, give me a thumbs up if I can move. Okay, this is just baby intro. Okay, so I'm going to elaborate, because I've already elaborated enough, but I have printed some of these notes for you, so I'm not waiting on you to write down a whole lot. Yeah.
If you have like 1 electron and hydrogen, which way would it spin?
Either way. Yeah, there's not a designation, 50-50 chance. All right, so I've already described to you the quantum number deal. That's the n number. So and this is actually what we spoke of with the Rydberg equation. As you increase the n number, you get from close to nucleus to farther and farther away from the nucleus. So if you're at n equals 5, you have more or less energy than an electron at n equals 1. More energy. Okay, so that's one thing you should note. My analogy to this is when you're at home close to mama nucleus, you're a really good boy and girl. You don't do anything bad. You are calm and collected. And when you're far away, maybe not as much. So crazy electrons out here, stable electrons close to the nucleus. Not only does that make sense in our analogy, but it should make sense in terms of the nucleus. What's the nucleus doing to this electron at n equals 1? It's attracting it, so it's holding it down. It's on lockdown, okay? The electrons out here is not being very well attracted, so it's not on lockdown. So it's able to be very excited. Yep, that's principal quantum number. Moving on. And you can see you can actually see the energy calculations here, but all they did was use the Rydberg equation. Say again?
How do you write it? Like the effective, like is there like a notation?
So we're not actually talking about effective nuclear charge at this point because that was just us understanding how far it is from the nucleus. We just know that if you're at n equals 1, you're close to the nucleus. If you're at n equals 5, you are far from the nucleus.
Like the
You write n equals 1, 2, 3, 4, like this. Okay? Okay, so I might erase this. Can I start to erase this? Okay. So with the angular quantum, or the second quantum number, you have really 4 numbers we work with. So if you're describing an electron in the s orbital, your second quantum number is a 0. Okay, so that's called the L number. So if you're talking about an S-shaped orbital, your L number is 0. If you are talking about a P-shaped orbital, your L number is 1. If you're talking about a D-shaped orbital, your L number is 2. And if you're talking about an F-shaped orbital, your L number is 3. So I always remember it as, I would put a fist up to remember this, because this looks like a what? Sphere, and this also looks like a 0. So that's how I remembered I started 0 versus 1 for counting L number, or for giving a notation for the L number. Now it's getting confusing. You're like, why are we giving numbers? Just wait, okay? So, as you know, because of the off-fall diagram we've spoken of, the S-shaped orbital is of lowest energy in a given sublevel. P, D, and F get in higher energy. So that's why we talk about, as we go from 0 to 3, you're increasing in energy as you go sequentially in those orbital shapes. And then, I'm not going to tell you the theoretical ones, they're more than what we need, but you don't really see numbers greater than 3, because we only really talk about levels up to F sublevels. Can we pass this? Okay, N number represents energy level, quantum mechanical, or principal quantum number. L number represents, so the orbital type, which we call the sublevel. So don't forget that sublevel term, because you might see that and be like, hold on, I forgot sublevel. This is just the style of orbital. Yeah. So the sublevel is the type of orbital shape. But what you'll notice is that since P, the shape is dumbbell, right? But there's 1, 2, 3 of them, so you don't know which one you're referring to until you get to the next number. We just know we're in the P sublevel, we're in the dumbbell-shaped ones. We just don't know if it's PX, PY, or PZ. Okay, that's our next number. So, with our pictures. Okay. Oh, and so, we draw all atoms like really circular, like little bitty spheres. It's because once you lay all of these orbitals on top of each other, they end up being very spherical in shape. So your S, your various P's and all the D's and all the F's, they end up like little balloon animals. And so we just draw them as spheres. That's why we draw them as spheres. Because in the end, you can't distinguish the orbitals from each other. Also, we can't really see inside the atom. This is theoretical. Okay. The magnetic, ML, magnetic quantum number describes which orientation you're actually talking about. So you might be in the P sublevel, but which of the P orbitals are you speaking of? So the ML number depends on the L number. So instead of reading all this off, I'm going to give you the examples. Okay. So S, how many different orientations can S take on? 1, okay? So if you have a L number of 0, your ML number, which means the orientation of that orbital, can only be one thing. It's going to be 0. And that's because the S orbital doesn't have any other orientation in space. The P orbital has an L number of what? 1, okay? So, but we know how many P orbitals exist. How many? How many? 3, right? So X, P, or PX, PY, and PZ. So there are 3 orbital orientations it can take on. So it should have 3 ML numbers. It goes from negative L to positive L. So from a negative 1 through 0 to a positive 1. Those are the ML numbers. So this was just a 0 because there's only one sphere. Those are the ML numbers for P because they have 3 orbital types. So how many ML numbers should I have for D? 5. They should represent the 5 orbitals in D. So D has a L number of what? 2. Remember, S is 0, P is 1, D is 2. And an ML number of plus, minus 2 plus 2. Which is negative 2, negative 1, 0, plus 1, plus 2. They're basically just giving us a secret code to represent every orbital in the atom. That's all these numbers are representing. So theoretically F, which has an L number of what? 3 should have ML numbers from what to what? -3 to +3, which would be -3, -2, -1, 0, +1, +2, and +3. How many orbitals are here? 7. How many orbitals are here? 5. 1, 3, 5, 7, right? So that's how we're correlating everything back to how we've been drawing the electron configurations and the orbital diagrams. Really, I didn't have to tell you all this for you to understand that, but now you should see a lot of correlations. Because if you take college chemistry in any way or form, you will definitely see these, and I don't want you to be like, hold up, you still didn't teach me this. So you need to see a little bit of the background. So can I go past 1, 3, 5, 7 for a second? Okay, so remember how we fill the orbitals? Like if I'm putting electrons in D block, how do I fill them? One at a time, right? So if I'm in D block and I'm in 3D, you guys know to put 1, 1, 1, 1, 1. And it's because all these, let's say, I'm just going to label them -2, -1, 0, +1, and +2. Those orbitals, they all have the same amount of energy, no matter if I put it in here or here, because they're all in that same sublevel, right? So we call those orbitals degenerate, meaning they have all the same amount of energy. So like a question might say, how many degenerate orbitals are in the p sublevel? How many degenerate orbitals are in the p sublevel? 3. How many degenerate orbitals are in the f sublevel? 7. It just means how many orbitals would you have drawn. But the word degenerate means what? Same amount of energy. So just some extra terms for you. All right, so the last quantum number, so the first one represented what? The N, which is also known as the energy level, also called the principal quantum number, okay? The second quantum number represented the sublevel, which gives us indication of the shapes that we're dealing with, called the, say again? I call it the orbital. It's called the angular orbital or angular quantum number, but we represent it with the letter what? L, and then the correct orientation of that orbital is the magnetic quantum number, which we indicate by ML, but it depends on the L number to give us the variation of where we can go to, which always will line up with 1, 3, 5, 7. So if you're telling me 6 for some reason, you're wrong. You got to go 1, 3, 5, 7. Okay. And then the last quantum number tells us is the electron spinning up or down, which we indicate as up, as a positive 1/2 spin, and we indicate down with a negative 1/2 spin. So if I ever say, you know, positive 1/2, just understand that's that's clockwise, that's up. And then if it's a negative, or it's a counterclockwise, which we spin down. So if you're in the orbital, how do we draw 2 electrons? Up and down, right? And it's because they have to be in their counter spin to create no magnetic field, so that we don't have a, is it para or is it dia that creates a magnetic field? Which one? Para, because dia just don't, right? Just don't do anything. Okay. All right, so now we're to the grand finale, which is this blue right here. Essentially, we went through all these numbers and this coding so that you could identify a singular electron in any orbital. And what you would give to me to identify that are 4 numbers. The N number, the L number, the ML number, and then the S. We call it the S because it's spin, or MS because it's once we've identified the orbital type, we can call it M, but I just call it S for spin. So once I've identified 4 numbers, I have pinned down a single electron. So those 4 quantum numbers are exclusive to that electron. What's exclusive mean? Like it's like a special set of numbers for that particular electron. It's very exclusive. No one else can get there. It's an exclusive number system for that electron. So that is truly what Pauli's exclusion principle is referring to, is the 4 quantum numbers that describe one electron. We also said, hey, you only put 2 Pauly pair, you only put 2 electrons in a given space, but it helps. This actually helps make more sense of it. And yeah, that's all I'm going to probably do for a quantum. I might do one more example. Can I go past this? This was on your note sheet, so you should be okay. This is on your note sheet too. This is just to show you the extreme nature of how this works. If you're an N1, what kind of orbitals are in the first energy level? What kind of orbitals? S-shaped orbitals, right? You can't have any P's, D's, and F's. So these are the only notations you could have. 1, 0, 0, and then either a plus or minus spin. Because there's a sphere which we assign a 0, and then we assign a 0 again for ML number, and then we could say a plus or minus spin. And then for the second energy level, you can have second energy level sphere, and then that's the orbital of the sphere. And then you can have like 2p, which is 2, and then L number 1, which represents the p sublevel, and then the 3 orbital types in p. And it builds and it builds and it builds. So that's what this little picture chart is supposed to show you. Yeah. It means the 2s. So like this is 1s, this is 2s, this is 2p, this is 3s, this is 3p, this is 3d. It says it actually right here. Yeah. I didn't see it till tonight. So it's supposed to give you, like, that's what we would normally write, but this is what we actually mean. Okay? All right, so stop there. Pull out your packet, probably the second page someplace. I don't think I need to tell you the rest of this. This is more reading. I'm not doing examples right now. Yeah. I'll go over some more of the vocabulary with this as we go. Find this. It's the second page. I'm going to see where we are in about 10 minutes. Okay, questions 1 through 12. It should start with electron configuration, quantum, and more. Third page. All right, 1 second. I only copied the first 8 up here, so when you get through with 8, we'll chat, but do through 12. Okay? You can write it on your paper, or you can.